Hi, everyone. So I'm going to switch to English. I'm Joseph. I'm a third-year PhD student at École Polytechnique in IPVF. And today, I'm going to tell you a bit more about how I'm combining physics modeling with machine learning to better understand solar energy degradation. So a fascinating fact that not everyone necessarily knows, in just 1 hour, we receive enough free solar energy from the sun to power our entire world for 1 year. But it's not enough to be able to convert the solar energy into usable electricity. We need to make sure that we can do this in a reliable and predictable way over at least 25 years. So the biggest challenge we have is degradation, because it means that we don't only need to constantly monitor the performance of the systems that we are installed, but when we design new solar cell technologies, we have to make sure that they can last for 25 years without actually having to wait 25 years to make sure that they will last this long. And the reason why degradation is so complicated is because it combines intrinsic and external factors that exhibit often intertwined behaviors. There are a lot of ways to study degradation in the lab, but they're expensive, they're time-consuming, and most importantly, they're expert-dependent. But luckily today, we have artificial intelligence, which can help us understand such complicated phenomena and accelerate much-needed solar energy breakthroughs by identifying hidden patterns in our data and allowing us to leverage the full potential of the information hidden in it. So in this context, my PhD consists of combining physics modeling with machine learning to better understand degradation at the solar cell, solar panel, and solar system levels. I've been working on a lot of projects during my PhD, but here I will just give you a brief overview of 3 of them. So in the first project, I show how we can use power production data. So it's data that we have and we can monitor from the comfort of our homes to extract valuable solar cell parameters. These parameters can give us an idea of what kind of degradation is happening on site early on, so we can perform preventive maintenance. They can also be used to simulate the behavior of our system, so we can forecast the energy generated by our system over time. And we can compare this predicted energy with the energy that a new system would generate to understand whether it's worth it to replace our old panels with new ones. So if you want to do this without artificial intelligence, you would need to uninstall your panels, take them to the lab, pay the lab to perform the measurements, and bring them back to the field, which is not very practical. So during the first year of my PhD, I showed how we can do this using a classical optimization algorithm. But then we realized that the algorithm we were using, and actually all the algorithms in the literature, are not suited to this kind of problem. So we decided to switch to something called Bayesian inference. And this was truly a revelation, because the Bayesian framework allows you to build probability distributions over your parameters. So you can find all the possible degradation mechanisms that could be happening on site, and you can know how likely each one is. So here, as you can see in these figures in blue, we get a probability distribution for every parameter. So I can tell you how confident I am about every value that my parameter can take. And then I can compare these values with the values in orange, which are the initial values, and see how my parameter has changed over time. Another way to think about Bayesian inference is by thinking of a coin. So if you have a coin and you know nothing about it, and I ask you, what are the chances of getting head when you flip your coin? You would say, I have 50% chance of getting head and 50% chance of getting tail. You start flipping your coin. Once, twice, 5 times, 10 times, you keep getting head. Oh, you're going to say, I'm getting lucky. Maybe I have more chances of getting head than tail. But then you continue flipping your coin 100 times, 500 times, 1,000 times, hoping the light will turn back on. And then you realize that half of the time you get head, half of the time you get tail. So you'll say, OK, so maybe after all, my coin is fair, and I still have 50% chance of getting head, 50% chance of getting tail. So similarly here, we start with a lot of uncertainty for the predictions that we're trying to make. But as we get more data over time, we can become more confident and decrease the uncertainty we have. So here, we get more data over time. But in your case, you can think about combining different measurements to increase the confidence you have in your predictions. In the second project, I use the same tools, but this time to extract material and interface properties of perovskite solar cells. For those of you who don't know, perovskite solar cells are the new hot thing in the field of solar energy. And it's very hard to extract these parameters experimentally. But once again, by combining physics modeling with machine learning, we can extract them from typical current voltage degradation data. And then we can understand which parameters are affecting degradation and which ones aren't. And in the third project, I'm basically taking the solar cells that we're testing indoor, and we're putting them outside in the real world to see how they would operate and try to understand the effect of external factors on their performance. We see the evolution of their properties over time and relate them to radiance and temperature. And we're doing this in an effort to bring these new technologies one step closer to the market. So in conclusion, all my publications and codes are open access. The Bayesian approach I'm developing is way faster than whatever you can find in the literature. I'm progressively updating it and uploading it on my GitHub page. and you can find it by scanning this QR code. Thanks.